Hi guys, welcome back to Data Every Day. Today we're looking at a data set of rent properties, well, just properties in the Netherlands, and we're going to try to be predicting the rent for a given property based on a series of data. Now this data is stored in a JSON file, so we're going to need to read it into a pandas data frame to really get a good look at it. You can see it has some features like for if it's furnished or not, latitude, longitude, postal code. Actually, has quite a few features. So let's hop into the notebook. We're going to grab the JSON file path up here, and we're going to load it in just a second. I'll just run through our imports. We're using NumPy and pandas for working with the data, for pre-processing, and building the pipeline. We're going to use the train test split function, ordinal encoder, one-hot encoder, column transformer, and pipeline object from sklearn. And our model shouldn't be linear model, it should be ensemble. Will be a random forest regressor, also from sklearn. Let's go ahead and import all of that, and now we'll use this to load in to the data frame using pandas.readJSON. So we'll just read that in, and let's store it in data. And let's see what happens. We may get an error, yep, and so when you see this error, usually what this means is you need to enable lines equals true here, because I believe it is in line delimited form, so you're going to need to just specify the argument at the end, and you should be fine to read it in. After that's done, we can take a look at it. And as you can see, it's actually quite a messy data set. There's a lot of raw data in here that hasn't been processed. I think a lot of these columns have a regular processed version of the column and then a raw version of the column. So we're not going to need a lot of the raw versions. There's also many columns in here I'm actually just not going to use for today's purposes, just because processing them would take a very long time, and I don't want to take too long doing this. And also they probably won't contribute too much useful information. I'm going to try to keep on what columns I can. But you can see we have 61 different columns. Each would require its own pre-processing. And you can see that there's quite a few missing values as well in the data. So let's create a function called preprocess inputs, and this is going to take in a data frame, make a copy of it, and then for the purposes of the video, like I said, I'm going to specify some columns to use. So let me just do that. I'm going to say use only select features. So I'm going to highlight particular features, which I'll just paste in here. These are actually just features that I went through and thought were a balance between useful and required a reasonable amount of pre-processing. Now, if I were really to build a fully functional model, I would try to squeeze every bit of information I could out of the data. I would not take shortcuts like this, but for the purposes of the video, I'm going to just use this select group of features. So let's encode, actually I'm jumping ahead. Let's look at it first. We're going to return df, and then let's get back the data here, store it in X, and pass in the data. So what this does is it takes the data frame and then selects only those features that we want, and so this is the data we're going to be using, which we called X. So there is a bit of pre-processing we have to do to this, but to really understand what we need to do, we should check a few things. First, let's check the missing values. So x.isInA.sum will tell us the number of missing values in each column. And so it looks like we actually have a bunch of missing values here. And the fact that we have 100 in each is actually very suspicious to me. Suspicious because when you have a bunch of columns that all have the same number, one after another like that, this can tend to mean that you have some bad rows where you have all missing values across, because it's very possible that there's 100 rows in here that have all missing values. So let's take a look at this. I actually noticed what the issue was. If we look at the original data, there is this column. Where is it? Called crawl status, I believe. Here it is. Crawl status. And so I assume what this column is saying is this uh, when the data was being harvested from the website, was it successful or not? So if we look at that, I'm not going to look at X. I'm looking at the original data, looking at the crawl status column, and looking at the unique values. There's done and unavailable. And if we look at the value counts here, we see there's actually 100 unavailable examples. And so these 100 unavailable examples actually are probably matching up with these 100 missing value rows. So we can verify this by taking data and using the query function to locate all of the examples where crawl status equals unavailable. And if we zoom over, sure enough, you can see there's all missing values for these particular columns. And so these are sort of you could think of them as bad rows. I mean, I don't really know if it's worth keeping these on. I guess it'd be up to you. We wouldn't really have too much performance decrease if we were to fill these missing values, because there are only 100 of them in a data set of 47,000 training examples. But because they're all blank, I think I'm just going to drop them. There's probably something wrong with these, and I don't want... I mean, I'm not sure if they're just incomplete, right? I can't really vouch for the quality of this data. And because we have so much other data available to us, I'm going to go and drop them. But this is more preference and based on what you think works best for the model. So to drop particular rows that match a certain condition, first we should get the indices of these rows. So these are the 100 rows that have crawl status unavailable. We can type .index to get the indices like that. And so if I take this and just put it in here and just change data to df, this should contain the indices we want to drop. So let's call this, what can we call it? Bad rows. Here's bad rows, that's the indices. So let's say drop bad rows. And we'll say df equals df.drop bad rows axis 0. Since 0 is the row axis. And since we're dropping rows, let's reset the index afterwards. Now, notice I'm doing this before we select the features, because we actually do drop crawl status from the group of features once we do this. So we drop all those rows, then we choose the features we want, and we should have something that looks like this, with the missing values are gone. So there's no more missing values, but actually there's just no missing values that have been encoded properly. So what I mean is, if we look at, let's get a little deeper look into some of these categorical columns. So for the numeric columns, we know they all have valid values. Because they have 0 missing values, when a numeric column has 0 missing values, it has to be a number, right? I mean, technically it could have something like -1 or something in there, which you may want to check for. Maybe a quick x.describe could show that for us. If we look at the min for all of the numerics, they all seem reasonable. The maxes all seem reasonable. So we'll just leave that. However, for the categoricals, you can see I had noticed this. It says unknown. And an unknown value is really a missing value. So it's possible that the missing values in here just weren't encoded properly. So let's look at it. We're going to make a dictionary that maps the column name to the list of unique values in a given column. So we're going to take x subcolumn dot unique and then turn it into a list, and do that for every column in the categorical columns. So we can get the categorical columns with x.select dtypes object dot columns. So that will just get the object columns. Alright, so the first one is city, and we can see all the cities here. There's quite a few cities, but I'll just zoom to the bottom. And this is the next one, which is the furnished column. And you can see we actually have a bad value there, which is a empty string. Going on, property type looks good. Internet, we have unknown. So unknown is a missing value. I will treat it as one. Now, some people don't, instead of encoding as a missing value and filling it, they'll actually just keep something like this, unknown, and then have that as its own category in the encoding. You can do this, there's nothing wrong with it. I tend to like to fill them, but it really is a matter of what you think works best. And if you really want to optimize the model, I recommend trying out different approaches and comparing the results. So for the purposes of the video, though, I will be encoding these as missing, and you can see there's quite a few of them. In fact, I believe there's almost all of many of these columns have an unknown. And looking at these values, it looks like the only bad values in here is the empty string and unknown, which appears in multiple columns. So let's go and encode those properly. Right here, let's encode improper values. So we're going to take the data frame and call the replace function, which allows us to pass in a dictionary with the mappings we'd like. And we're going to replace an empty string with a missing value, numpy.nan. And we're also going to replace unknown with numpy.nan. Now if we run this, if we scroll down to the bottom again, you can see we now have missing values where we used to have the unknowns and the empty string. So if we run this, we should be able to see the missing values. And I want to get a sense of how many these are in terms of the rest of the data. So we can use the mean instead of the sum to see the percent of missing values in each column. So this says 0.7%, 17%, 16%, 18%, 16%, and 16%. So these are all reasonable numbers. Usually if it goes over 25%, then I'll drop the column because it's too many missing values. But these are reasonable. So why don't we go and fill them with the mode of each column. The reason I'm saying mode is because none of the numeric features have missing values. We checked that earlier, but you can see the area, which is numeric, the latitude, longitude, and the rent all have 0 missing values. So we're going to fill with the mode because you can't take the mean of a categorical. For example, let's look at the living room feature here. If we take the mode of this, it's going to return the most frequent value. Actually, it's as a series. You can see not as a string because you could have multiple modes. So if we want to get the first string that shows up, we'll just subscript at 0, and then we get the string. So let's use this to encode. So we can fill missing values. And now because we know that all the rest of the columns have all the rest of the columns are categorical, we don't have to type out all the column names. We can actually just say missing value columns is equal to, and if we want to get all the columns that have missing values, we can type x.isNA again, sum over the rows like we did before. Ask, is it greater than 0 for each column? And here a true means there's at least one missing value. We can use this true-false series here as an indexer for x. Sorry, not for x. For x.columns. So as long as this is the same length as this, we can just use these true-falses as indexers for this. So we'll index x.columns using this true-false array, and that will give us just the columns that have at least one missing value. So let's use this up here. Just change x to df, and these will be the missing value columns. Then what we'll say is for every column in missing value columns, we'll take the column and we'll fill it, its missing values with the mode of the column. So df subcolumn dot fill na will fill the missing values, and we'll fill the missing values with df subcolumn dot mode. And we do have to subscript with 0 like I showed before. Okay, now let's take a look at x. And again here, if we scroll down to the bottom, you can see there's no more bad values here, no more empty string, no more unknowns. And here as well, you can see we have no more missing values. Alright, so missing values have been dealt with, and the data is looking pretty clean. Now we're going to be doing a pipeline model today, so I'm going to leave the data in a human readable form before we build the model. So this is useful for when you are deploying a model and you want the user to be able to enter their own inputs. You'd want to save the data in this form when you pass it into the model so that these make sense to the user. So let's do this. the last thing to do is to split the data frame. So split df into x and y. Y is going to be what we're trying to predict, so that's going to be the rent column. So that's df sub rent, and then x is the rest of the data, so we'll just drop rent from axis 1. Then we'll do our train test split. That will return 4 new sets of data, which is xtrain, xtest, ytrain, and ytest. And for this, we're going to use the train test split function from sklearn, where we can pass in x and y, specify a train size. I'll give it 70%. Keep shuffle equals true, so that it'll shuffle the data before it makes a split. And we'll give it a random state as well, so we can reproduce the shuffle. Let's go ahead and return these down here and get them back over here. And look at xtrain. Alright, so now the data's been shuffled. We're working with 70% of the data, and we don't have the rent column anymore. Ytrain should just be the target values associated with each of these examples. Alright, now let's do training. We'll build the pipeline and train. So building pipeline and training. Alright, so to do the pipeline, we need to consider pre-processing steps and then create the model. So we'll work backwards. We'll work from the end because we know we want a random forest regressor as our model. So what I'll do is put this at the end of the pipeline. So our model is going to be a pipeline whose steps include a random forest regressor. Now we need to include this in a tuple with a name, so we'll call it regressor, and it's a random forest regressor. So right now this would work just as a standard random forest regressor, but the pipeline allows us now to put more steps in before we actually pass it into the model. And we're going to have to do that because, yeah. Okay, just give me one sec, let's see. Okay, so now we have to consider what steps do we need to apply before we do the regression. So we need our input, let's look at xtrain, to be in all numeric form. Now we don't have to scale this data for for today's model because we're using a tree model, and tree models don't require scaled data. However, we do need to process all the categorical variables and turn them into numeric variables. So how do we do this? First, we should check out which how many values are in each column. So I'm going to make a dictionary similar to the one we did earlier, where we map the column, this time not to a list of the unique values, but to the number of unique values, which we can just by taking the length of xtrain. Let me think. Actually, should be doing this for x, for the whole data frame. So let's return x at the end here, just so we can see. X is just the whole data before the split is made, right? Get it back over here. And the reason for that is because when we're looking at this, we want to be seeing the whole data. So we take a given column of x, look at its unique values, take the number, and do that for every column in x.columns. Now we're looking at the categoricals, right? So we should actually do x.select dtypes object.columns. And what I'm looking for here is any column that has 2 values. And the reason I'm looking for that is because if a column has 2 values, it needs to be encoded with a single column because, well, it's just it would have duplicate information if we were to one-hot encode it. So let's look at one-hot encoding with pandas.getDummies, and let's take in the property type. So this is the kind of encoding we're going to use for the categoricals, and you can see that a 1 in a given location represents the original value of that example. All the rest will be zeros. And this is fine for categories that have 3 or more values, but when you have one with 2, you can see it becomes very redundant because every time you have one value, you just have the opposite value in the other column. So we're going to want to do technically one way we could do this is just to drop one of the columns at this point, like that, and this would be a proper encoding. But we're going to make it a little more interesting. We're going to use an ordinal encoder, which essentially will just map each value to a new integer. So it'll map one of the values to 0 and one to 1. So let's use an ordinal encoder here. That comes from sklearn. And we're going to enclose this in its own pipeline as well. And call it ordinal. Like that. Okay, and the reason for this is we want to embed this pipeline in a column transformer so that we can tell the model which columns to apply this ordinal encoding to. So we'll call this binary transformer. And we're also going to do our one-hot encoder. So the one-hot encoder will do that dummy column thing that I showed. We'll call this nominal transformer, since this will be used on the nominal features, which will also be a pipeline whose steps are just a one-hot encoder. I'm just going to include sparse equals false so that we don't get back a sparse output from here. Alright, and then what we're going to do is take our binary transformer and our nominal transformer and feed them into a column transformer that takes in a set of transformers and then specifies which columns to use them on. So let's call this our preprocessor. So first we have our binary, and this is going to be using the binary transformer we specified. And we also need a list of columns to apply this to. So the binary is just being used on columns with 2 values, which actually is just the internet column. So we'll just put internet in there. And then we're going to, after that, use the nominal transformer on all the nominal features. Now, to get the nominal features, those are just all of the rest of the categoricals. I'm just going to paste them in here for time. So they're called nominal features. Let's just call this nominal features. Now we have a preprocessor. One thing I have to point out is that we should definitely specify remainder equals pass through here. What that means is all the columns that were not touched by the preprocessor will still be attached to the data. Then we've built our preprocessor and we want to put that into our final pipeline. So what this will do now, when the model sees data that looks like this, first thing it will do is run it through the preprocessor, which applies ordinal encoding to the internet column and one-hot encoding to the nominal columns. And then, once it's properly encoded, it'll pass it into the regressor, make the predictions, and train the model. Okay. So let's run this, and we'll fit the model to the train set. Alright, so our model is fit. Now let's get some results. Alright, so this is a regression model, so we're going to get 2 metrics, which will be the RMSE and R-squared score. For each of these, we're going to need a set of predictions. So I'm calling model.predict on the test set. We do have an issue here. Alright, so this is actually a very important issue. So it's saying it found unknown categories. And so the reason for this is we did a train test split, and we had the city column. Where is it? Here, the city column, which had like 700 different categories in it. And we're pretty much bound to end up with some values in the city column that are only in the test set and not in the train set. The problem with this is that when we do the one-hot encoding, we're only fitting this to the train set. So the model creates columns for those values that were originally in the train set, but if it finds new values in the test set that weren't originally there, it's going to throw this error. So the one-hot encoder from sklearn actually has a built-in mechanism to handle this. You just pass in handle unknown equals ignore. Ignore. And that will tell the model just ignore it if you find one of these values. Don't throw an error. With that, let's retrain the model and see if we get results that way. All right, and now let's try getting some predictions. And there we go. Okay, so this generates predictions for each of the test examples. I'm going to store this in ypred. So ypred is our predictions, and ytest is the actual values. Now, the hope is that these values are going to match up with these. They're going to be close enough. It's looking okay based on just these right here. These are looking pretty good. But let's calculate the average error across all examples by taking the test values, subtracting the predictions. And so this is the error for each example. This is how far off we are in either direction. However, we want to get the average error, and if we were to sum these up and and divide by the number that we have, we'd have a problem, because that would it would give us the average at around 0, because the negatives would cancel out some of the positives. And you can see that if we take numpy.mean of this, we get something somewhat close to 0. It's not really telling us how our model is doing. So let's consider how we can avoid this. One way is to square these errors, and we have them all on the positive scale. So then we take the mean. This would be the mean squared error. And so this is our average error across all examples, but in the unit of the squared target variable. So I think we're dealing with euros. The Netherlands currency is the euro. So I believe the rent is being given in euros. I'm going to assume that. So this is actually squared euros, right? It's because we squared it. So we can return it to the original unit of euros by taking the square root after that, and we have it now as 156. So this is telling us, on average, we're about 156 euros off a rent prediction, which is fairly good. Especially if we look at the test set ytest.describe, we can see the distribution of the variable has a minimum of 1, maximum of 5,000. And the distribution looks something like this, with a median of 550, a 75 percentile of 800, and a 25 percentile of 390. So you can sort of visualize that distribution a little, and being off by 156 is really not all that bad. It's by no means perfect, but it's definitely, at least it's operating with some degree of accuracy. Okay, so the other way we can analyze the model is by using an R-squared score, which is it's a way of comparing a model to another model. And in the case of the R-squared score, it's actually comparing it to the baseline model, which is saying what model would you use if you had no input data available to you. So if we look at ytest, if we had no x-test, just ytest, the best model we could come up with is to predict the mean each time. If we predicted this value for every single example, we'd get some set of errors for that as well. Sorry, it should be ytest minus ytest.mean. So these are the errors, while errors calculated for the baseline model. Similarly, we could do it for hours, and instead of the mean, we just do ypred. So these are the errors for our model, the errors for the baseline model, and like we did before, we're going to square them both and compare them. So we want some sort of comparison between ours and the baselines. We want to see how much better our predictions are than the baseline predictions. So instead of taking the mean, I'm just going to take the sum of each, and the sum down here, and we can compare these sums. So we compare the sum of squared errors, and one way to compare them is just to put them in a fraction, with ours on the numerator and the baselines on the denominator. And that will give us something close to 0 when we have very low error, or rather when we have much lower error than the baseline. On the other hand, if we have much higher error than the baseline, then this thing will become increasing towards infinity. When we have equal error to the baseline, this thing goes to 1, and we'd have a 1 there. Now this is almost the R-squared score. but R squared score is 1 minus this value. And that's a useful way to do it because then if we have 0 error, this whole fraction goes to 0, and 1 minus 0 is 1. So the best R squared score you can get is 1. On the other hand, if we have much more error than the baseline model, this fraction goes to infinity, and 1 minus positive infinity is negative infinity. So the R squared score takes on a range of values from negative infinity until 1. And so that's a nice way to visualize how much better your model is than another model. So let's look at this R squared score. We have an R squared score of 0.85, which is saying we have a 85% reduction in error from the baseline model's error to our error, which is pretty good. So you can think of the RMSE as sort of an absolute metric. It evaluates your model absolutely in terms of the unit of your original target variable. And the R squared score is like a relative or comparative metric because it compares your model to another model. So we'll just put these and print them out. RMSE, we'll display to 2 decimal places and format with RMSE. And R squared score, I'll say score. We'll format this to 5 decimal places. Pass in R2. There we go. So on average, we're 156.94 euros off, and we're 85% better than the baseline model. Alright, so thank you so much for watching. That was some of today's video. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.